Hello, my name is Jenny Kuriloff, and today I'm going to talk to you about climate change, how it's changed before, how it's changing now, and why today is different. Throughout Earth's history, climate has changed a lot. Over the eras, Earth has seen tremendous variation in temperature and environment. In the Pleistocene epoch, occurring 2.6 million years ago, Earth experienced its most recent ice age. Ice sheets covered not just Antarctica, but big parts of Europe, North America, and South America as well. Sound chilly? It sure was. And yet, despite the cooling climate, Earth was bursting with life. Not only was Homo erectus, the ancestor to humans, evolving, but many other early hominins inhabited the Earth as well, like Homo neanderthalis. Okay, so now we know that humans, or at least their ancestors, could flourish even in the coldest of environments. But what about the hottest? The hottest period in Earth's history began 55.8 million years ago with the dawn of the Eocene epoch. The Eocene epoch is thought to have been 9 to 14 degrees Celsius hotter than today's temperatures. That's really hot. Climate scientists postulate that the reason for this unprecedented warmth was high levels of carbon dioxide in the atmosphere, between 1,000 and 2,000 parts per million. By comparison, the amount of CO2 in the atmosphere in 1900 was only 300 parts per million. In this warm, humid climate, lush vegetation overtook the Earth and ice was minimal. During this time period, flora and fauna flourished. Early ancestors of horses, rhinoceroses, tapirs, deer, cattle, sheep, whales, and bats evolved on the Earth, as well as primates that are still alive today, like the tarsier. Now, you might be wondering, isn't global warming dangerous? I thought too much atmospheric CO2 was a bad thing. How could life have flourished under the conditions of the Eocene? And the answer to that question is time. In the case of the Eocene and other periods where life was in abundance with CO2 in the thousands of parts per million, oceans, atmospheric gases, and most importantly, life had millions of years to adjust to high levels of CO2. With millions of years of slowly rising CO2, Earth's chemistry can remain in balance. But what happens when CO2 rises rapidly and organisms don't have time to adjust? Unfortunately, the result is catastrophic. During the Permian and Triassic periods, rapidly rising CO2 levels resulted in mass extinctions that wiped out a majority of life on Earth. Does that sound scary? It should, especially when modern-day CO2 increases that typically happen over tens of thousands of years have taken place in the last 70. Now, you might be asking, how could we possibly know what the temperature was a million years ago? As it turns out, climate scientists have a lot of cool ways of estimating historical temperatures. To explain how it works, we need to understand a little bit of chemistry. An atom is composed of 3 parts: protons, neutrons, and electrons. The number of neutrons in the nucleus of an atom determines its isotope. Oxygen-16, for example, has 8 neutrons, while oxygen-18 has 10 neutrons. Because oxygen-18 has more neutrons, it's actually heavier than oxygen-16. This means that in the ocean, oxygen-16 will preferentially evaporate, as it's lighter than oxygen-18. In a glacial period, oxygen-16 that evaporates will be trapped in glacial ice and will not return to the ocean, so more oxygen-18 will be left in the water. As it turns out, microorganisms called foraminifera use the oxygen isotopes to build their shells, and when they die, their shells fall to the ocean floor, creating a sedimentary layer. Scientists examine the concentration of the isotopes in their shells to determine temperature. More oxygen-16 in their shells corresponds to warmer temperatures. So now we know one way of many that scientists estimate ancient temperatures. Now that we've examined past climate change, let's talk about why the rapidly climbing CO2 emissions of today are a problem. When solar radiation enters Earth's atmosphere, about 30% of the radiation is immediately reflected back out into space by clouds, ice, snow, sand, and other reflective surfaces, while the remaining 70% is absorbed by the oceans, the land, and the atmosphere. As these surfaces heat, they release the energy back into the atmosphere and into space. However, gases in Earth's atmosphere have the ability to trap radiation, preventing it from escaping. As CO2 concentrations increase, greater quantities of radiation are trapped within the atmosphere, causing the planet to heat up. Global warming causes a multitude of problems. Wildfires become increasingly common, which not only destroys lives and biodiversity, but also releases more carbon into the atmosphere, perpetuating the cycle of warming. Additionally, the warming environment causes water to expand and ice to melt, leading to sea level rise. While rising sea levels might not sound like a problem, in reality, it can overtake coastal cities and drown communities, endangering millions. Additionally, as CO2 continues to rise, we experience more extreme weather events, including heat waves and droughts. The direct cause of warming and the host of consequences that follow it is the burning of fossil fuels. But how do we know that there isn't another reason? Let's investigate some other forces that can affect temperature. One force described by Milankovitch that affects Earth's temperature is the shape of Earth's orbit, also known as eccentricity. Earth's orbit fluctuates between an almost circular orbit and an oval-shaped orbit. When Earth is closer to an oval-shaped orbit, more solar radiation reaches the Earth as it approaches the Sun, resulting in warmer temperatures. The cycle from a circular to elliptical orbit takes 100,000 years, and while we currently have a near elliptical orbit, we are on our way back to a circular orbit. Eccentricity, combined with tilt and axial precession, Milankovich's other predicted cycles, do a good job of explaining long-term climate change. Over the last 500,000 years, Earth has been subject to ice ages punctuated by very hot periods and high concentrations of CO2. However, these changes happened at a very slow pace, on the scale of hundreds of thousands of years. The rapid increase in temperature and CO2 of today have happened in the last century. Additionally, current trends in our planet's orbit point us in the direction of cooling, not heating. Therefore, today's rapid temperature increases cannot be attributed to the Milankovitch cycle. Other potential factors, like solar radiation released from the sun and CO2 released from volcanic eruptions, don't appear to account for the change we're seeing today. Today, 97% of climate scientists agree that modern-day climate change is primarily human-caused. I hope that in today's video you learned how climate change today is different from the natural changes of Earth's past, and that you understand why it's a problem. Thank you for listening, and I hope you enjoyed.